Chapter 6.3, Proving Identities. Equation versus identity. An equation is only true for certain values of the variable, whereas an identity is true for all values of the variable. To prove an identity is true for all permissible values, both sides of the identity must be expressed in equivalent forms. One or both sides of an identity must be algebraically manipulated into an equivalent form. Operations cannot be performed across the equal sign. Verifying versus proving an equation is an identity. Simplify the expressions on each side of the identity independently. Example, determine the NPVs for tan x cos x over cosecant x equals 1 minus cos squared x. So where would we have fractions? First of all, we have a cosecant x on the bottom of a fraction. We also have tan x, and tan x is sine x over cos x. Which means that cos x cannot equal to 0. Cos x equals 0 at pi over 2 and 3 pi over 2. Therefore, x cannot equal pi over 2 plus pi n, where n is an element of the integers. Then cosecant x is equal to 1 over sine x. So sine x cannot equal 0. When is sine x equal to 0? Sine is the y value on the unit circle. That equals 0 here at 0 or here at pi. So then we have that x can also not equal 0 plus pi n, where n is an element of the integers, or just pi n, where n is an element of the integers. So here we have the general statements for the NPVs for this question. Verify the equation may be an identity by either graphing it or choosing a value for x. So if you graph it and see that the graphs lie on top of each other, then it should be an identity. Or if you pick a value and sub it in. Example, let's check the equation for pi over 4. I'm choosing pi over 4 because then my x and y values are the same. They're both root 2 over 2. That'll make my life easier. Then we have tan of pi over 4 times cos of pi over 4 divided by 1 over sine of pi over 4. And here it's not asking us to do anything algebraically, so we can use our graphing calculator. I need to be in radian mode, which I am, and then I want to do a fraction. On the top of the fraction, I want tan of another fraction, math, enter, pi over 4, move out of that fraction, move out of that bracket, and then do cos of the fraction, pi over 4 again, move out of that fraction, move out of that bracket, then move down to the bottom, and we have the fraction 1 over sine of fraction again, pi over 4, and then equals, we get 0.5. Then we want to sub that value into the right side as well. 1 minus cos squared pi over 4. 1 minus bracket cos fraction pi over 4. Move out of the fraction, move out of those brackets, close the bracket around the cos, and then square it, and we get 0.5. So the left side equals the right side, which tells us this could be an identity, and then we would need to prove it. Now prove the identity is true for all permissible values of x. The left side is tan x cos x over cosecant x. The right side is 1 minus cos squared x. The left side looks more complicated. Let's simplify that and see what we get to. Tan x is sin x over cos x times cos x divided by cosecant is 1 over sin x. On the top, I can divide out the coses, and I'm left with sin x over 1 divided by sin x. Dividing by a fraction, I want to multiply by the reciprocal, so sin x times sin x over 1, which gives us sin squared x. And we want to turn sin squared x into 1 minus cos squared x. Remember our Pythagorean identity, we have that sin squared x plus cos squared x equals 1. So if we subtract cos squared x from both sides, we get sin squared x equals 1 minus cos squared x. So then we can write sin squared x equals 1 minus cos squared x. So we get the left side is equal to the right side. And let's just restate our non-permissible values in case you're looking back while doing a question and don't notice them up above. So our NPVs were that cos x cannot equal 0, therefore x cannot equal pi over 2 plus pi n. N is an element of the integers, and sin x cannot equal 0 since we have cosecant in this identity, so x cannot equal 0 plus pi n, where n is an element of the integers. Strategies for proving identities. Work with one side of the equation at a time and start with the more complicated side. Keep an eye on the side you're not working on. This becomes your target. Try to factor an expression, add or subtract fractions, square a binomial, multiply by the conjugate of either the numerator or denominator, or create a monomial denominator. Try to use the fundamental trig identities, reciprocal, quotient, or Pythagorean identities. See which trig functions are in the final expression you want. If nothing seems to work, try converting all ratios to sines and cosines. If it contains a 1 and a squared trig ratio, look at Pythagorean identities. When both sides of an identity are complicated, it may be easier to prove an identity by showing that both sides simplify to the same expression. Remember to state your NPVs for the identity, and the proof is over when the expression on the last line of one side looks exactly the same as the expression on the last line of the other side. Example, algebraically prove each identity for all permissible values of the variable. State any restrictions on the variable. We have 1 plus cotan theta over cosecant theta equals sine theta plus cos theta. The left side, 1 plus cotan theta over cosecant theta, and the right side is sine theta plus cos theta. The left side's more complicated, so I'm going to simplify that one. Cotan theta is cosine over sine, so this equals 1 plus cos theta over sine theta divided by cosecant is 1 over sine, so 1 over sine theta. Let's write this 1 as a fraction with sine as the denominator so I can combine those two fractions. That would be sine theta over sine theta plus cos theta over sine theta, and then the bottom is still 1 over sine theta. Then the top becomes sine theta plus cos theta over sine theta divided by 1 over sine theta. I'm dividing by a fraction, so I'm going to multiply by the reciprocal to get sine theta plus cos theta over sine theta times sine theta over 1. And then I can divide out sine theta, and I'm left with sine theta plus cos theta, which is the right side. So now that I've gotten the left side to equal the right side, my proof is done. And next I want to state the NPVs. What do we have as denominators? We have sine here for cotan, and we have sine here for cosecant. So they're both the same. Sine theta cannot equal 0. When the sine equals 0, sine is the y value, so that equals 0 at the x-axis, which is here. So when theta equals 0. And when theta equals pi, therefore theta cannot equal 0 plus pi n, where n is an element of the integers. Cos x over 1 minus sine x and 1 plus sine x over cos x. They look equally as complicated, so pick a side to manipulate. I'm going to go with the left side. We have cos x over 1 minus sine x, and the right side is 1 plus sine x over cos x. I can't change cos or sine. I do have a binomial denominator, so I'm going to multiply by the conjugate. Then I get cos x over 1 minus sine x times 1 plus sine x times 1 plus sine x. That gives me cos x plus cos x sine x. And on the bottom, 1 times 1 is 1. 1 times sine x is plus sine x. Negative sine x times 1 is minus sine x. And then negative sine x times positive sine x is negative sine squared x. Then I get cos x plus cos x sine x over, simplify the bottom, we get 1, middle terms add to 0, and then we have 1 minus sine squared x. But from our Pythagorean identities, 1 minus sine squared x equals cos squared x. So the top is still cos x plus cos x sine x, and the bottom becomes cos squared x because we have the Pythagorean identity sine squared x plus cos squared x equals 1. If we subtract sine squared x from both sides, we get cos squared x equals 1 minus sine squared x. So we can replace 1 minus sine squared x with cos squared x. Then I see that I can also factor out cos x from the top. Cos x times 1 plus sine x divided by cos squared x. And then I can divide by cos x on top and bottom. And that leaves me with 1 plus sine x over cos x, which is the same as the right side. So I've proved it. Next, I want to state my NPVs. So let's look at all the denominators throughout the proof. On the right side, we have cos x. Then cos x cannot equal 0. When does cos x equal to 0? That's when x equals pi over 2. And when x equals 3 pi over 2. Then the general statement for this NPV would be x cannot equal pi over 2 plus pi n, where n is an element of the integers. On the left side, we have 1 minus sine x for a denominator. So 1 minus sine x cannot equal to 0, which means sine x cannot equal 1. When does sine x equal to 1? Sine is the y value of points on the unit circle. Y is equal to 1 up here at pi over 2, but that NPV has already been taken care of by this statement here. And then also on the left, we multiplied by the conjugate of 1 minus sine x. So we had 1 plus sine x as a denominator. That can't equal 0, which means sine x can't equal negative 1. When is sine x equal to negative 1? The y value is negative 1 on the unit circle at 3 pi over 2. That point is also taken care of by this statement for NPVs from cos x can't equal 0. So we don't need to add any further statements for the NPVs. Prove that 1 over 1 plus sine x equals secant x minus sine x times secant x over cos x is an identity for all permissible values of x. The right side is definitely more complex. So the left side is 1 over 1 plus sine x, and the right side is secant x minus sine x secant x over cos x. I see right away that I have a secant x in each term on the top, so I can factor out secant x to get 1 minus sine x divided by cos x. Then secant x is a reciprocal trig function, so I can write that as 1 over cos x times 1 minus sine x, all divided by cos x. I can write the top as one fraction. 1 times 1 minus sine x is 1 minus sine x over cos x, and all of that over cos x. Then I can multiply by the reciprocal since I'm dividing fractions, so 1 minus sine x over cos x times the reciprocal of cos x, which is 1 over cos x, which gives us 1 minus sine x over cos squared x. But cos squared x from the Pythagorean identity, we have sine squared x plus cos squared x equals 1. So I can rewrite cos squared x as 1 minus sine squared x. Then I get 1 minus sine x over 1 minus sine squared x. This binomial is a difference of squares. So I can factor that. We get 1 minus sine x over 1 minus sine x times 1 plus sine x. And then we have 1 minus sine x, 1 minus sine x divide out, and we're left with 1 over 1 plus sine x, which equals the left side of the equation. So I've proven the identity. Now I need to do my NPVs. What do I have in my denominator? On this side I have cos x all the way along, cos x, cos x, cos x, cos x, and cos squared x. So for that side, we have that cos x cannot equal to 0, which we've seen many times now. So x cannot equal pi over 2 plus pi n, where n is an element of the integers. And on this side, we have 1 plus sine x as a denominator. So 1 plus sine x cannot equal to 0, which means that sine x cannot equal -1. When does sine x equal -1? Sine is the y value, so it equals -1 down here, which is 3 pi over 2. And every time that we get back to that same position, so 3 pi over 2 plus 2 pi n, where n is an element of the integers. But if we notice, 3 pi over 2 would actually be part of this. So I don't actually need to write anything extra for sine not equal to -1. Prove the identity sine 2x minus cos x over 4 sine squared x minus 1 equals sine squared x cos x plus cos cubed x over 2 sine x plus 1 for all permissible values of x. Both sides are fairly complex, so I'm going to do some manipulating to both sides. The left side is sine 2x minus cos x over 4 sine squared x minus 1. Sine 2x, I can look back to find my double angle identities. My double angle identity for sine is 2 sine A cos A. So I have 2 sine x cos x minus cos x over the bottom 4 sine squared x minus 1. That's a difference of squares. So that I can factor that to 2 sine x plus 1 and 2 sine x minus 1. On the top, I can factor out cos x. We get cos x times 2 sine x minus 1 over 2 sine x plus 1 times 2 sine x minus 1. Then I have factors of 2 sine x minus 1 on top and bottom that I can divide out, and I get cos x over 2 sine x minus 1. That's a much more simplistic form. Let's see if we can simplify the right side down to that as well. We start with sine squared x cos x plus cos cubed x over 2 sine x plus 1. On the top, I can factor out cos x. Cos x times sine squared x plus cos squared x over 2 sine x plus 1. Oh, on the left side here, that should be 2 sine x plus 1, not minus 1. Then on the right side, on the top of my fraction, sine squared x plus cos squared x, that's the Pythagorean identity. That equals 1. I have cos x times 1 on top, which is just cos x, over 2 sine x plus 1. Then the left side and the right side are the same. And we want to state our NPVs. The denominator on the left is 4 sine squared x minus 1. That cannot equal to 0, which means that sine squared x cannot equal to 1 over 4. Take the square root of both sides, but we don't know if sine started as positive or negative, so plus minus square root, we get sine x cannot equal positive or negative 1 over 2, so plus minus 1/2. When is sine equal to 1/2? Sine is the y value, so positive 1/2 here, negative 1/2 here. That's our smallest of the special angles, so pi over 6. And it's in every quadrant since it's both positive 1/2 and negative 1/2. So we would have to write two general statements for this NPV. We would have x cannot equal pi over 6 plus pi n, where n is an element of the integers. So that would be the angle in quadrant 1 and also pi away in quadrant 3. And then for quadrant 2, that angle would be pi minus pi over 6, which is 6 pi over 6 minus pi over 6, which gives us 5 pi over 6. So, and x cannot equal 5 pi over 6 plus pi n, where n is an element of the integer. So that would be the angle in quadrant 2 and also pi away in quadrant 4. Then we have another denominator. We have 2 sine x plus 1. Let's check to see if that gives us any more NPVs. That cannot equal to 0, which means that sine x cannot equal to negative 1/2, but we already have that covered here with sine x cannot equal positive or negative 1/2. So that's not going to add any more NPVs. So those two statements right there are all we need for NPVs. That brings us to the end of Chapter 6, Lesson 3.